And the answers are here. So let's have a look at the first one. So question 1, it says we're given S, which is the distance, the arc length around the circular track. We're told the radius, and we're trying to find the angular displacement. And very often it will say radians and degrees. So we need to be able to convert between the two. So we can see it's going to be this first formula, theta equals S over R, and it's just the ratio of the arc length, 150, divided by the radius, 50. So that will give us a nice number of 3 radians. Bear in mind that radians, there's no actual unit for radians because it's a ratio of lengths. But sometimes, just to remind us that it is angular displacement, we could write RAD for radians. Sometimes, more of a maths thing, they write a little c with superscript. But yeah, we would normally write RAD in physics. And then we can convert it by multiplying by pi and divided by 180, and you should get 172. Question 2 says find the angular velocity if we have 30 minutes for every full cycle. So here we're going to use v is equal to, we're going to use this second one, omega is equal to delta theta over t. So all we need to know is the time period. So we could work out the frequency and use 2 pi f, but we're going to use this one here. So in one complete cycle, we have 2 pi radians. So the angular displacement is 2 pi, and the time period is, well, we're given there 30 minutes. We could write it in as radians per minute, but we would normally use SI units. So 30 times 60 would give us radians per second, and we get this fairly small number here of radians per second. Angular velocity, and now we're given the frequency of rotation. So we could again use the one we've just used, but it would make more sense to use 2 pi f. So again, we know 2 pi is the number of radians in one complete cycle, and we're told the frequency of rotation is 0.42 per second, or 0.42 hertz, or 0.42 cycles or revolutions per second. So we just multiply 2 pi by our number here, and that would give us 2.64 s to the minus 1. We could write radians, even though that's not actually a unit, just to remind us that we're actually talking about an angular displacement here. And question 4, using the final one, v is equal to r times omega. So we are told the radius is 4 centimeters. So the radius of the CD might be larger, but the radius of the point we're interested in is given as 4 centimeters. And we're told that it's rotating at 430 RPM. So you're probably familiar with, you've probably heard of RPM, revolutions per minute. So we'd have to convert that into revolutions per second, or radians per second. So 430 revolutions, so multiply by 2 pi would give us the number of radians per minute. And then we need to divide that by 60 to give us the radians per second. So that's our first thing to do. And you would be expected to work with RPM and convert that into radians per second. So the final stage, we're trying to find the velocity, the linear velocity. So we can just multiply the radius. So we could convert that into meters, 0.04 multiplied by the angular frequency, and we get 1.8 meters per second. And as we would expect, the velocity will increase with the radius. So even though the RPM, the angular frequency, stays constant, as you move further outwards from the center, then the velocity will increase in proportion to the radius.